Hey everyone, welcome back, and today let's solve Leetcode problem 1800 titled Maximum Ascending Subarray Sum. A good problem and a good continuation of yesterday's problem, keeping track of current sums and subarrays at a specific time in each iteration of a solution. But more on that later. Let's go ahead and get into the problem statement. So we're given an array of positive integers nums, and we have a very simple output problem statement, right? We simply have to return the maximum possible sum of an ascending array subarray in the input array nums, right? And what the problem really means rather, by ascending, basically it means in increasing order. And the definition of increasing order is basically a subarray, or generally just an array where each element is smaller than the element after it and larger than the element before it. So to kind of put that into context here, assume we had an input array of per se 1, 2, 3, 4. This would be an example of an ascending array. Why? Because every element is smaller than the element after it adjacent to it. And every element is also kind of very similarly greater than the element before it. 1 is less than 2, which is right after it. 2 is less than 3, which is right after it, and so on and so forth. 3 is bigger than 2, which is right before it, and 2 is bigger than 1, which is right before it, and so on and so forth for 4 and 3 as well, right? That's kind of the definition of what an increasing or ascending array really is, right? And again, kind of gives us the definition of a subarray as well. Basically, it's a contiguous sequence or portion of numbers or elements in an array, right? And effectively, again, what they define ascending to be, like we just talked about, a subarray where basically we have elements from index L to R. Every single value for per se nums at index L is going to be less than nums at index L plus 1. In other words, for all indices I, where I is between the range of those two indices L and R of that subarray, we know that nums at I is always going to be less than nums at I plus 1, which is simply the I plus 1th or the next element right after it. And note that a subarray of size 1 is ascending. Actually pretty important for not only this problem but the solution as well, because just think about it, right? If we had a singular element or a subarray with only a length of 1, a singular element with it, like 1 or even like 2, these individual elements, or these subarrays with length 1, they also would technically be considered ascending for this problem, which is also very important to note, because we know off the bat, since we want to return the maximum possible sum of an ascending subarray, we know that the minimum length of any ascending subarray, at worst case, is going to be at least 1, because we know any element by itself is going to be considered ascending for this problem's context. Okay, well, with that out of the way, let's go ahead and dive straight into the examples here. Again, so in our example 1, we have our input array nums to be 10, 20, 35, 10, and 50. And in this case, we actually have an output of 65. There are actually several ascending subarrays in this input array nums. One of them would actually be 10, 20, 30. But if we summed up the elements of that ascending subarray, we would get a sum of 60. Now, that isn't actually the most optimal subarray or sum to rather choose from, because we can actually pick the sum or subarray sum 5, 10, 15. Note that it is contiguous and it is ascending. 5 is less than 10, which is less than 50. Right? And in this case, if we summed up the elements here, we'd actually get 65, and that actually is the ascending subarray of this input that actually has the maximum sum. This guy had a sum of 60, this one 65. The maximum of those two would indeed be 65, and so that is why the output for this example is going to be 65. So in example 2, we have our input array nums to actually just be 10, 20, 30, 40, 50. In this case, as we actually kind of iterate through this array, we see that every single element is actually less than the element after it, following that ascending or increasing order logic. And so we can actually take the entire input array and just sum up the elements of that, because the entire input array is actually in ascending or increasing order. And in this case, the sum of this maximum subarray sum would actually be 150. And so that is the reason why we have a maximum sum output of 150. And finally, for example 3, we have our input array nums to be 12, 17, 15, 13, 10, 11, and 12. And in this case, our output is actually 33. Again, we have multiple different ascending subarrays in this input array nums. Of course, the base would be just all these single elements by themselves. But of course, we also have things like 12, 17. We also have something like 10, 11, 12. Or even just 10, 11. But let's just think about it. we wouldn't be helping ourselves at all or gaining anything by not including this 12 when we take in the subarray 10, 11. We know that taking another element that's still in ascending order is going to do nothing but help us, because we're guaranteed that all the elements in this input are going to be positive. And so knowing that, we know that we can have the maximum ascending subarray sum to basically be these three elements, 10, 11, 12, which in this case are going to give us an output of 33. It'd simply be 12 plus, or rather 21 plus 12. Now, this also is in ascending order, 12, 17, but that subarray that's ascending actually only has a sum of 29, which is less than 23, which is less than 33, and so this is the most optimal subarray to choose that has the maximum sum in this input array, which is actually 33 for our output. So for the constraints here, again, basically the length of our input array nums is not going to exceed 100, which is a pretty small input, at least relatively, in terms of data structures and algorithms and time and space complexities. And we're also given that any value or index at nums I in the input array nums is also not going to exceed 100. And so we know that we are given pretty flexible constraints. We don't really have too tight of values for the input here, and so we don't have to have the most crazy fast of solutions in like logarithmic time or anything like that. Linear is also a perfectly good solution. And that actually brings me into the solution for this problem. How can we do this? Well, think about it. This really is just a one-pass solution, right? We basically iterate over our input array nums, and while we're actually forming an ascending array, we simply increment or keep adding on to the current sum of that current subarray and maximize the current sum of all the ascending subarrays in our input array. Because like we discussed before, when we have 10 and 11, which are part of an ascending subarray, there's no reason not to include this 12, because we're guaranteed that every single integer is going to contribute positively, because it is a positive value to the current sum of any ascending subarray. And so while we do have ascending subarrays, basically every element is greater than the element before it, we can continuously keep adding on to the current sum as an ascending subarray and maximize the ascending subarray sums for all the ascending subarrays in our input. And to better make sure of that, let's go ahead and dive straight into the code here. So what I'm first actually going to do is actually initialize my maximum sum and my current sum. And in fact, a nice way to do this in Python isn't really available, I don't think, in other languages, at least for the most part here. We'll also get a current sum, and I'm actually going to initialize both of these values to nums at index 0. Now, really what the point of this really is, basically maximum sum and current sum, pretty self-explanatory. Current sum is literally just marking or representing the current sum of the current ascending subarray that we're forming or building elements from in this specific iteration of the input. And the maximum sum is, of course, the maximum sum that we want to actually output. Right, that's actually going to be the maximum sum that we find in all of the ascending subarrays, which we effectively are going to return the maximum of. Right, and of course we simply I just initialize this to nums at index 0, because of course we're going to be starting with the initial element in the input array and building on from there. That isn't the most important to really know. I think you should still be fine initializing these to both 0 and moving on from there, but that's how I initialize them, because of course we are actually starting from the initial input, or from the initial element in our input array. So now let's actually iterate through the input. So for I in the range of the length of our input array nums. But something very important to note here, since I am actually initializing these two variables starting off with nums at index 0, I don't have to actually start from nums at index 0, because that would basically be me over counting that initial element. And so I'm actually going to start from the first index and go up until the length of our input array nums. Right, in this case, starting from the first index or the second element of my input array. Now, the very first thing that I'm going to check is the current element, nums at index I, is it actually part of my current ascending array? Now, how do I actually check if it is actually a valid element that's part of my current ascending subarray in my input array nums? Very simple. If the current element, nums at I, if it's actually greater than the previous element, nums at I minus 1, I know this is part, or it is forming an ascending subarray, and so I can increment my current sum for this current ascending subarray with the current element nums at I, because I know that it does actually form or contribute to the current ascending array. Because again, like we discussed, in an increasing order or ascending subarray, every single element is larger than the element before it. Every single nums at index I is going to be larger than nums at index I minus 1, or the element before it. And if that's the case, meaning it does actually kind of contribute or be part of an ascending subarray, this current element, then we want to add it to the current ascending subarray sum, which is going to be stored in the current sum variable. But what if this isn't the case? What if nums at index I is less than or equal to the nums at index I minus 1? That means it isn't actually part of the current ascending subarray. It disrupts or interrupts the current subarray that's ascending, and so we have to stop building that current ascending subarray, and we have to start from fresh from the current element. And the way we can do that is simply get the maximum sum, and first maximize it with, of course, itself, because we don't want to make it smaller, and the current ascending array sum, and then we reset, or kind of have that resetting logic where we reset our current ascending subarray to only be the current element itself, because we know it isn't part of the previous ascending subarray, because that current element nums at index I isn't actually greater than the element before it, nums at index I minus 1, and so we have to start fresh from the new ascending subarray with the current element, or from the current element. And so we'll set current sum to now just be the initial element nums at index I, and start building from there from the future elements and future iterations of this input. And effectively, once this for loop is actually done executing, we simply return the maximum of either the maximum sum or the current sum at the end of this iteration for the current sum at the very last ascending subarray. Now, if I were to submit this, this would actually be accepted, and there should be a valid solution. And as you can see, this really is just about as efficient as you can get. So, to kind of reiterate what our code does actually as a whole, effectively we're iterating through each element in the input array. Now, if the current element is greater than the previous element, per se this 30 and this 20, great, we know it does actually form or contribute or is a part of the current ascending subarray. And so we can increment the current ascending subarray's sum with the current element and simply move on to the next iteration. However, if the current element, let's just say in this case, 5 is not greater than 30, well then we know that it wouldn't actually be part of the current ascending subarray. We have to then maximize the maximum sum with either itself, just in case we don't want to make it smaller, with its current element or current value, or the current ascending subarray sum, which in this case would be 60. So let's kind of simulate this in example 1. We go from 10, okay, sure, 20 is still greater than 10, perfect, added to the current sum. Now we're at 30. So we started off with 10 at our current sum, then we went to 20 plus 10 is 30, then we went to this 30, which is still greater than this previous element 20, and so now we have 60. But in the next iteration, we have 5. 5 is not greater than 30, and so this basically disrupts the current ascending subarray sum. We basically have to maximize the maximum sum currently to whatever it's stored to be the maximum of either itself or this current subarray sum, and move on. Basically start fresh from this element as the new starting element from our current ascending subarray, because we know that this isn't actually a part of the ascending subarray from 10, 20, and 30, and so we reset or start fresh as 5 as the new starting element, and simply move on from there from future iterations and maximize the maximum sum with all of the ascending subarray sums and get the maximum value from there. So in this case, that's basically how this code works. For the runtime complexity, it's actually going to be a simple one-pass linear time solution, a big O of n solution. We really only iterate through each element exactly once. That's what we do this singular for loop here, and believe it or not, the memory or space complexity is actually big O of 1. We aren't actually using any extra data structures or any auxiliary memory. We're only using a couple integer variables like maximum sum and current sum, which don't actually scale directly proportionally with the input size, and this is actually a big O of 1 or constant time solution hence. So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel, and without further ado, I will see you guys in the next video. Bye bye.